So today we'll begin with mathematical modeling. So based from definition shown here, okay, let me start first. Based from the definition provided here, mathematical modeling is actually a set of equation, normally in the form of a differential equation, which is in the form of d over dx, dy over dx, dv over dt, and so on. So that is in the form of differential equation. So the equation will represent the dynamic of the system, how the system behave. How the system behave, it will create a proper an equation with respect to that movement. So in practice, we especially in control, we require that the modeling sometimes require for assumption, such as initial condition, what happened to the system during initial condition at specific temperature, and so on. So this one you will see later. And then how do we solve the mathematical modeling? We use a special tool in control system, tool that we call Laplace transform. The equation will be in the form of Laplace, and then from there we will manipulate in order to obtain the transfer function. And lastly, we need to have a balance between the simplicity and also the accuracy. How do we simplify our system, and also we need to achieve a specific degree of accuracy based from that transfer function in order to conduct analysis. So looking at this figure, we have two figures, A and B. I think this one you're already aware. We have input and also output, and then we have the middle is the system. And also we have B. This happens when we have multiple subsystems inside the system. As you can see, the input still remain the same, input and also output. Okay, but the subsystem will increase depending on the system actually. So figure A and figure B, you can see from here the input remain the same and also the output, except for the subsystem inside this system. So referring to figure A, this one, referring to figure A, so you can see this is the common representation. I think you are the last Monday, you've already learned. Basically, GS is typical or common representation of a system. Capital G, and then open and close bracket. Inside this bracket is actually small, small case s. Everything here is small, except for the first word here, capital R, and also capital C. So we have input, which is represented by RS, and also output represented by CS, and then the system is GS. So based from this figure, we can obtain a mathematical equation whereby GS here is actually equal to output divided by input, the ratio between output and also input. So when we replace this output and input, we have output is equal to CS, and also input is equal to RS. So this one would be the common mathematical equation for a system. For this case is the transfer function. So looking at this definition, the transfer function of a linear system is the ratio between input and output of the Laplace transform. The notation here, the value here in the form of Laplace. So the ratio between output and input in the form of Laplace. And then from this equation, we can manipulate, as you can see from this bottom here. The output is actually, we can obtain the output, CS is equal to RS multiplied by GS. So from here, we can manipulate. We can also obtain input, which is RS is equal to CS over GS, and so on. So this equation, the basic one, just inform us that GS is equal to ratio between output and also input in the form of Laplace. So for transfer function, we have two type of transfer function that we need to understand. The first one is proper, and then the other one is improper transfer function. So what happen between improper and proper? We look at the number of or the degree of numerator to denominator, the top and the bottom one. Numerator for top and then the denominator for the bottom one. Proper transfer function happen when the degree of numerator lower than the degree of denominator. For example, we have transfer function here 1 over s. So the root here is actually more than the on the denominator side, and also this example shown here 1 over s plus 3 multiplied by 1 over s plus 5. So the degree of denominator is actually higher than numerator. So when this happen, it is we call this a proper transfer function. And also for improper, you can see here, it is actually the opposite from the first condition here. The numerator is actually higher than the denominator side. So you can see from this example, s plus 2 over 1. So you can see from here, numerator is actually higher than denominator. The degree, the root here is actually higher than the denominator side. So there are 4 properties that we need to learn. You need to learn related to transfer function. The first one would be it is the transfer function is it is only possible for linear time invariant system only, or LTI system. Linear time invariant is actually a system that can produce output depending on the input, provided that the system is bounded by linear and time invariant system. So the first one, and then from this transfer function, we can analyze. So we can know whether the system stable or not. And then from here, we can identify poles and zero from this transfer function. And then from there, we can also start assume in order to move on to the analysis or the manipulation. We can also normally we make several assumptions. One of them is by assuming that the initial value is actually 0. So this one, the all 4, the number 2 and 3 and 4, you will learn later. This one only apply to transfer function. So we look at the application first. There are 2 types of application that you can see here. The first one is open loop transfer function. I think you already know open loop without feedback. So from open loop transfer function, if you obtain an open loop transfer function, we can do this 4 method. We can apply transfer function toward this 4 method. The first one, we can analyze the steady state error. And also for number 2, 3, and 4, this the step, the number here involve graphical method. So we can use open loop transfer function to draw locus, to draw dot plot, and also to perform Nyquist plot. 2 and 3 you will learn later on the future topic. And also for closed loop transfer function, if we do transfer function, closed loop transfer function, we can analyze the stability of a certain system by using this method, row service criteria. That one also you will learn later. But right now we look at the application related to our field, which is electrical network transfer function. These are some examples that we can obtain. So basically, transfer function we can generate or we can manipulate, we can obtain coming from physical system. So the physical system we can represented by linear time invariant differential equation. So from this, we model as in a form of transfer function. So we look at first at electrical network transfer function. There are other applications that you can see here: translational, rotational, system with gear, electromechanical, and also electric circuit analog. So the first one, we look at electrical network transfer function first. So how do we obtain a transfer function for electrical network? So basically, we need to know the type of the network, electrical network consists of. So from here we know that the electrical network consists of passive network and also operational amplifier circuit. So these two you will learn later. But right now we will look at passive network. So what is passive network? Passive network is actually the typical example. The most common one would be these three components: resistor, capacitor, and also inductor. So this one you will learn. You will learn on the next slide how to obtain for these three component, passive component. But first we look at the method on how to obtain this transfer function on electrical network. So there are four methods that you can see here. The first one, we try to sum up voltages around the loop. How many loop? And then the sum of voltage must be equivalent to number of loop. So sum of voltage around the loop or sum of current at each node. So there are two methods, sum of voltage or sum of current. So this technique depending, so you can use any method that you feel comfortable, either sum of voltage or sum of current. And then from here, we try to manipulate in terms of algebraic manipulation, and then the whole equation we must make it equal to zero. The result must be equal to zero. And then from there, we write the differential equation of the circuit. And then from the second method, we transform using Laplace transform of the differential equation. We transform the equation from previous step into Laplace transform, and then finally we manipulate in order to find transfer function. So looking back, we refer back at these three basic components here: capacitor, resistor, and inductor. These are the relationship that we can see with respect to this component. The first one will be voltage current. This happens when voltage output V is equal to 1 over C integral part of I tau over I tau d tau. So this is in the form of voltage current, and then this is in the form of current voltage. I is equal to C multiplied by this is the differential equation dVt over dt, and then voltage charge, impedance multiplied by charge, and also impedance, and also CS. So you can see from here, you need to know this is the value, the form here, the notation here is fixed. So you need to be aware. So from these three components, we establish first the basic representation in the form of voltage current. By taking the voltage current representation of capacitor Vs is equal to 1 over Cs multiplied by Is, and also resistor, inductor. The transfer function would be Vs over Is is equal to Zs, which is the impedance. So this one depending, you can see from the example shown later. So depend on the question provided. So for typical circuit, the transfer function would be the impedance for this network. So the first thing that we do, once we have established this representation value, we redraw back the original network by showing all the variables such as Vt, It, and also Vct. This is in the form of differential equation in time domain. And then we transform in the form of Laplace. So you can see from here, V small case v become capital, I small case become capital I, Vc become capital Vc. But the S remain small case. And then from here, we replace the common component value with their respective impedance value. Okay. The replacement is similar to the case of DC. We represent the resistor with their respective resistance value. So you can see from this example. Find the transfer function relating to the capacitor, which is here, Vc. to the input. So this means that the question require us to find the transfer function relating to VC. This is the output with respect to the input VC over VT in this figure below. So we can, so for this example, example 3.3, we can start by referring back to the method, to the previous method, as you can see from here. Okay, so we can choose, we need to choose which method that we are comfortable with, either sum of voltage or sum of current, and then write the differentiation and then transform the Laplace differentiation, and then finally we solve for transfer function. But the first thing that you need to know is one already shown here. Okay, so the ideal method would be we need to replace the component value with their respective impedance value. Okay, so from this figure, if we follow method from previous slide, so we can see we need to replace every variable from time domain to Laplace, and then we draw back the circuit. We replace the time domain value into respective Laplace transform, and then the value of the component also we need to replace. Okay, so I show you this example first. This one we just replace based from previous example. The first one is actually inductor. Inductor, the impedance value would be LS. So we just replace L here with LS. So I just put S here, small case S, LS, and then R remain the same, nothing changes. So R here would be the same, and then C would be 1 over CS. So we just replace 1 over CS, 1 over CS, that's it. And then for this I, we need replace to capital I, and then S, and then we see here we need to replace with capital VC, S, and then VT we need to replace with capital V, S. That's it. So if we refer back to this explanation, once we have transformed, we withdraw and then transform the representation of variable from time variable into Laplace, and then replace the value. So the question asks us again, find the transfer function related to capacitor voltage VC over Vs. So we need to find VCS over Vs. Okay, in the figure below. So this one is a single loop. It's a single loop electrical network. So we can proceed by finding the sum of, shown here, sum of voltage around the loop. So so the current here is flowing clockwise direction. So this means that the current here, you can see the arrow here, the current will meet with the negative value of Vs. So it will be, so this one, erase first. We obtain first because the electrical network shown here is actually consists of one loop, so we just derive. So we find the total sum of voltage from here voltage from here, and also voltage from here. So we start first with Vs. So Vs would be negative, negative Vs, and then we'll go find with ILS multiplied by IS, and then plus R multiplied by IS, and then plus 1 over CS multiplied by IS. And then the whole sum must equal to 0. So this one would be equation 1. Okay, so we can check. So in the form of this, we can check here. Okay, voltage. Voltage representation of each component. So we have potential voltage from capacitor, voltage from resistor, and then voltage from inductor. So we just copy this value, LS multiplied by, for example, this part, LS, IS. So LS, IS is voltage for inductor. So the rest remain the same. This is for the first equation, and then we need to find mathematical equation with respect to VC. Okay, because we want to find the ratio between output here to input VC. So we find here. So from here, VC is actually 1 multiplied by CS. So from here, VC S equal to 1 over CS multiplied by IS. Okay, so this one would be equation 2. Okay, so from here we obtain the value of IS. So IS would be equal to, so from 2, IS is equal to CS multiplied by VCS. Okay, so we can call it equation number 3, and then from here we can substitute into 1. Okay, anything that is IS we include. So I have already, so you can see from here, for example 3.3 I already completed. So this is how we manipulate. You can use any method that you feel comfortable with. So for this one, so you can see from here, once, okay, this is the VS, and then substitute, and then the final value would be VC over VS. So it is 1 over CS LS square plus CSRS, and then plus 1. So you try first. And then if problem, maybe we can see after Hari Raya break. So we move on. We move on to more complex circuit. How do we solve complex electrical network? Normally happen when we have more than one loop, time dependent, voltage dependent, source, and so on. So how do we solve? To solve for complex electrical network, especially the network that have multiple loop and also node, we normally use mesh analysis. So there are up to 6 steps that we can use. The first one, we replace passive element value with their impedance, as shown based from previous example. L is equal to Ls R is equal to R, C is equal to 1 over Cs. The three common passive component with their respective impedance, and then from there replace all the sources and time variable with their Laplace transform, the previous one. Okay. L, Ls, R, C, 1 over Cs. And also V here become capital Vs, capital Is. Anything that is in the form of time variable or time domain, okay, which is shown here with shown here by the T character here. This is in the form of time domain or time variable. So we need to convert that to Laplace. And then assume transform current and current direction of each of the mesh. So okay, we can assume the direction of the current in each of the mesh. If we have more than one loop, so you need to create or assume direction of the current in each loop. And then write Kirchhoff law around each mesh. We find out the total sum of all the components inside each of the loop. And then solve simultaneous equation for the output. And then lastly, we form the transfer function. This one, 5 and 6 will be the manipulation. How do we manipulate? Okay, so equation 1, equation 2, equation 3, you need to manipulate. Okay, so this one, we will do it after Hari Raya break. Okay, this one is too complex to show online. So we move on to the other part, which is a electrical network transfer function. This type consists of operational amplifier. So why it is related, the operational amplifier related to control system? Why? Because it is the building block in order to implement transfer function. The gain. So the gain from control system, if we transform or translate that into actual physical component, it is actually in the form of gain. So the best representation would be the use of op-amp. So there are 4 characteristics that you can see here from an op-amp. That is the differential output is actually V2 minus V1 in time domain. And then the impedance at input here is actually high, equal to infinity. This one for ideal case, number 2 and number 3 for ideal case. Z1 here is actually high, too high or infinite value. And then low output impedance, Z0 inside here, Z0 is really equal to 0. So we have two assumption here. This one for these two assumption, both for ideal condition. And then the last one, high constant gain. The gain here is equal to infinity, also for ideal case. So in the end, if we want to obtain the output here, it is actually equal to A, the gain. A, the gain equal to V0 T in the form of time variable or time domain equal to A multiplied by output, the differential input, V2 minus V1. The whole thing multiplied by gain. So this is the the benefit of using operational amplifier. We can amplify or we can increase the input up to certain value depending on the supply. So this is the advantage of using operational amplifier. So we look at some of the configuration that we can obtain transfer function. The first one would be inverting mode. This one happen when you can see here the input is connected to the negative side of this op-amp. So output would be negative A multiplied by V1 in time domain. So this one is the basic one. We also have another configuration which is you can see from here the feedback. The feedback is connected to a resistor, and this resistor connected to the output, and also VI or the input signal connected to V1. So for this typical configuration, the Transfer function is given by the ratio between V0 over Vi. So V0 over Vi is equal to negative Z2 divided by Z1, the ratio between Z2 and Z1, negative value. So this is in the form of inverting connection here. So you can see here the connection input connected to negative side of this op-amp. So other than that, we also have non-inverting input connected to the positive side of this op-amp. So what happens if we have this type of configuration? The feedback is still the same, connected between output and also the negative part of this op-amp. And then other connection, we have capacitor, a resistor connected directly to the ground. So for this combination, we can obtain this the transfer function given here by the value, the ratio between sum of Z1 plus Z2, Z1 plus Z2 divided by Z1. If you see here in the form of this one is similar like voltage divider method. Okay, so for example, 3.5, this one I will show you but just partial part. Okay, so you can see from here, we try to identify which configuration does this circuit belong to. So you can see here the connection is, the input is connected to the negative side. We have we can summarize. We have two passive component. We can summarize this as either Z2. We can summarize the whole thing here as Z2. So you can see here. Here we can represent the whole impedance here as Z2, and then this one we can represent the whole impedance here as Z1. Okay, so you can see this is actually Z1, this is actually Z1, and then this is actually Z2. So you can see the typical representation would be in the form of this one of inverting operating amplifier. So as you can see here, we already know output over input is really the ratio between Z2 over Z1. So we go back to this example. So we can say that we can derive that the output V0 S over VIS is actually the negative. So you can see here the negative part of Z ratio Z2 over Z1. Negative part of Z2 over Z1. So in order to obtain Z1, we need to solve. We need to solve this part first. The capacitor connected in parallel with the resistor. So we can obtain Z1 first. Z1 is equal to 1 over Z1. 1 over Z1 is equal to 1 over 1 over CS plus 1 over R1. R1. So from here you can obtain Z1. Z1. And then we can also obtain Z2. Z2 is equal to the connection shown here. R2 connected in series with capacitor. So R2 plus 1 over C2S. C2S. This one is actually C1S. C1S. So once you obtain this, you just insert Z2, insert here on the top, and then Z1 you insert on the bottom here, Z1 here. So Z1 would be 1 over the whole thing. C1s plus 1 over R1. So you can solve. So that one will give you some idea on how to solve example 3.5. So we move on to example 3. Okay, so this one, the more complex one, I think I better show you after the break. Okay, so we move on to differential equation. So what is differential equation? How do we obtain this differential equation? This one will be explained on this slide. So based from previous explanation, we know that physical law process, when we model, it should be in the form of differential equation. So we also have two type of physical process. That is the first one, mechanical and also electrical. The mechanical system, we can obtain the transfer function by applying Newton's law, while the electrical part we just apply Kirchhoff's law. So this one you already know. This is in the form of differential equation. Voltage across inductor, so it's in the form of L multiplied by the differential dit over dt. And then for radioactive decay, dN over dt. These are some of the example in the form of differential equation. This one in the form of mechanical, dV over dt multiplied by infinity multiplied by d square u over dx square plus the whole thing equal to 0. So these are some of the example that we can use differential equation to model physical system. So again, so from here, how do we solve differential equation? So in the form, so you can see from here, if the equation is in the form of exponential, we can replace it by in the form of differential or exponential e to the power of at over dt. So in the end, we get a is actually the differential part of multiplied by the exponential of e to the power of at. And also if the signal is in the form of sinusoidal, we can do this representation of differential equation. So you can see from here, it is in the form of negative a square multiplied by sine at. So from here we can represent in the form of exponential to the power of negative j omega t or e to the power of at. So these two we will see later. So right now it is part of the introduction. So again, from the previous part, how do we perform manipulation in order to solve or to obtain transfer function? So the method, the tool that we use is Laplace. So what we do is that the Laplace transform relate time function to frequency dependent function of a complex variable. So meaning that if we have a signal or system in the form of continuous time xt, we can use Laplace to create an equal value which is in the form of frequency dependent. So we can see here in continuous time, the signal is in the form of time domain or xt, and then for z transform, this is in the form of discrete time. It is given by xn. So basically, Laplace transform is defined by this function here, L, Laplace transform of function with function of time. So we transform the function of time in Laplace using Laplace. So it is equal to Fs. So Fs would be the function of the equation in the form of Laplace. This one in the form of time. Then we transform using this Laplace equation, and it is actually equal to the integration part starting from 0 up to infinity, the function of this part in time domain multiplied by exponential to the power of s negative s st to dt. Okay, whereby s here s equal to sigma plus j omega, where sigma is a complex variable. So you can see from here, real part and also imaginary part. So when we know ft, when we know the equation of the function in time domain, we can find the function of fs, which is called the Laplace transform of ft. So how do we transform back from Laplace equation to time domain? We can use this method, the inverse Laplace, the inverse Laplace of function of a Laplace transform equal to ft function in time domain. So it is actually given by this equation 1 over 2 pi j integration part from sigma minus j infinity to the limit sigma plus j infinity, the function of Laplace multiplied by exponential to the power of st to ds. So this happen when ut is equal to 1, ut is equal to 1 when the time is greater than 0. So when the time is less than 0, the value of ut should be 0. Okay, should be 0. So these are the transform table for the most common signal. We have from step, ramp, and so on up to the sinusoidal, cos, and so on sine. So in the form of time domain, this one impulse up to the Laplace transform value of each of the signal in time domain up to Laplace value. And also we have a characteristic theorem. This one, what happen if the function is in the form of the first one would be we have the addition of two function, time shift theorem, scaling theorem, and so on. So this one would be the rules, the rule for the theorem part, differential part. So I think I better pause here. I better pause here. So we have some time. So I think we better go back to previous example. We go back to chapter 2. We go back to chapter 2. Okay, this one as promised. I will show you some of the example, how to solve for some of the example. This one. Okay, we look at example 2.1 first. We look at example 2.1. This one is quite direct. How do we simplify this block diagram? How do we simplify this block diagram? Multiple subsystem. Here you can see starting from system here, and then here we also have feedback. Okay, so we refer back to the rules. Rules given here. First check for series block, and then parallel block, and then check for feedback loop. And then if there is difficulty with takeoff point or summing point, we either shift to the right or shift to the left for both point, and then we repeat again. So this one already shown here, no need further explanation. So we go to example 2.1. So you can see we check first. We check first for series and also parallel connection. So from here you can see we can solve this part. I think we can solve this part. Yeah, so we can solve this part cascade. So the value here would be G2S, G2S multiplied by G3S. Okay, so we already solved this one. And then this one is quite direct. So you can refer to the previous rule, table of rules shown here. Here. Okay, so you can see from here, if we have multiple subsystem concentrating on a single point here, so it is actually total sum. So again, we go back to this example 2.1. So we can simplify. We can simplify the whole thing. So you can see here, we can simplify the whole thing. So they both the same, except for the value here. Except for the value, H1 is actually negative, H2 is actually positive, and H3 is actually negative. So we can simplify the whole thing here. So this part is actually equal to negative H1 S plus plus H2 is positive, H2S H2S, and then we have minus H3S. Okay, so in the end we can solve. So in the end, the circuit can be something like this. We can redraw back in the simplified version. This one plus going to one sum. This is actually this is G1. G1S, and then we have G2S, and then we have G3S, and then here we have H1S minus H2S plus H3S. H3S. So go back. So this one, output CS. Okay, so you can see here, the first one, if we refer back to the example, H1 is actually negative. So H1 is actually negative. So we want to put negative here. So H1 should be positive. And then H2 should be negative. And then H3 also should be negative. Why? Because we already represent by the signal. So RS here. RS. Okay, and then from here you can solve. You can solve this one. You use a feedback equation, and then once you have obtained here, okay, first you find this part first. Solve for this part. Okay, using feedback equation. And then once you have obtained this, you can start by solving for cascade between here and also here. Okay, so I think that one already solved for example 2.1. And if you go to example 2.2, reduce the block diagram shown in figure below to a single transfer function. Again, you can use you can apply the method. The method here, first we need to identify first cascade and also parallel connection, and then after that we check for feedback, and then if we have problem with respect to shown here, we have difficulty with takeoff or summing, which either shift to the right or shift to the left for both point. Provided that if we have difficulty, if we have problem to solve from rule 1 to rule 3. So we go back to this example. Okay, this example. So you can see from here, first we identify cascade connection first. So I think no cascade here, no cascade, and also we don't have, we have one parallel, one parallel connection here. But you can see from here, okay, we have problem here. We cannot solve okay, connection between here and here. So we have at point V3 and also point V4. We cannot solve directly. Why? Because we have problem here. So therefore, it is a peak of point. So the best option would be we can either shift this part to the front of G2, and then after that we can solve. You can solve everything. So the best option would be here. Okay, we connect to here. So this one would be clear. Yeah, the problem here would be clear, and also this one should be was 1 over G2S. Okay. Other than that, after that, I think you will have no problem. Okay, since we don't have a cascade connection, we just solve this part only. This part only. So this one would become 1 plus 1 over G2. Okay, if we want to solve this, so this one will become this part. This part will become, if we solve first, 1 plus 1 over G2S, and then we go here. If we go here, okay, since this one we already solve. Okay, so we go from here. This one is G2. Okay, G2S. Okay, so this one, and then this part is actually H2, H2S. Okay, so I just shown you this part only. The rest will be the same. This one would be the summing point. Okay, so okay, we can check again. We try to check first. Okay, 1 over G, so G2. So G2, so you can see from here, when we shift this peak of point to the front of G, it will be here. So we have 2 points here, 2 peak of point. Okay, so this one go here, and then this one go to the bottom here. We also have new one. Okay, this one for H1. Okay, so I think that one could give you some idea on how to solve. So for example, 2.2, so we move on to the signal flow graph. So remember, for signal flow graph, for branches, it only represents system, and also for signal, represented by node. So these are 2 things that you need to remember. Other than that, not related. So system is actually represented by branches, and also signal represented by node. So if we see here, so you can see the signal we represent by node, the system is represented by branches. So if we have 2 signals, so there will be 2 branches. If if we have 2 systems, there will be 2 branches, 2 signal, 2 node. Except here, so this one should be 3 node. Same goes here, 3 systems, so there will be 3 branches and 3 signal 1, 2, 3, 4. 1, 2, 3, 4. So they will be three note. Sorry, 4 note. Okay, 4 signal here. We have 4 signal, so they should be 4 note. Same goes for here. So you can see we have RS signal going to ES signal. So you can see no representation for signal flow graph. So for this case, not valid. So not valid. So typically system and also signal only. So this one summing peak of point not related. So how do we replace this? How do we transform this into signal flow graph? So you can see from here, RS is going to the ES, RS is going to ES. So this part, nothing here, nothing here. So we can always put one. So feedback here going to ES. So feedback here going to ES. The direction need to focus on the direction and also the value negative should be negative HS. Same goes for here. We have RS going to ES. So we have other than summing point, we don't have any system, we don't have any signal, so we can put one between RS and also ES. And then G1 going to LS, G1 going to LS. Yeah, so LS start from here, so we can put this as 1 also. And then from LS going to G2, here going to G2, and then G2 going to YS. And then going back to this feedback loop. So we go back to example 2.3. This one quite direct. Again, this one we just RS signal we replace with node. This one replace with node. This one replace with node, and this one replace with node. So we have this one is CS. This one is X1S, and this one is X2S, and then this one is RS. And for G1, G1 you just represent with branches. Need to be aware of this direction of the sign. So in the end, if we combine, so this should be one node going to G1S. This one is RS, and then going to the second node, which is X2S, going to G2, G2S, and then from here to another node, X1S, going to G3, going to G3S, and then this G3 going to node CS. Okay, so this one quite direct. So this is the signal flow graph representation. So this one quite direct. So you can always refer from this table. Okay, from this table already shown here. So so this one, I think we better look at this one. Example 2.6. 2.6 again, better. Okay, so you need to identify first signal, and also which is signal and also which is system. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. We have up to 10 signal. And also we have G1, G2, G3, 3 subsystem, and then we also have H1, H2, H3, three feedback. So they will total 6 subsystem. So we should have 6 branches. So again, R1 we need to identify first. R1 we have one node. R1 V1. So this one should be to the value of 1, and then G1 to V2. G1 to V2, and then V2 to V3. V2 to V3. This one, the value here is actually 1. And then going to V4, G2, and then V4 to V5. V4 by this one, we put 1, okay, and then cascade, parallel form. So V3, we can always put either V4 or V3. So no effect. So this one is actually 1. Okay, positive, positive 1. The parallel, and then V5, and then V5 to C. Yes, this one is G3. And then from here, C to H3, and then to V8. This one is H3, and then V8 to V5. V5 here, so you can always put, okay, you can put here. Okay, but right now the value here is actually negative, so it should be -1. And then this part go to H2, 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 H2 go to V7. So V7, H2, so V7 can go either V2 or V3. Okay, so we can put this one. So again, the value here is negative, so it should be -1. And then we also have this one. Okay, so V4 go to H1. This one is actually H1, and then this is V6. V6, and then going back to it can be either V1. Okay, again, this one negative, -1. Okay, so in the end, so this is the form. So if we want to make it nice, R1, V1, V1, R, and then this is 1, and then we have G1, and then V2, and then we have V3, this one, and then we have G2, and then this one V4, and then between V3 and V4, another one, this one should be 1, and then V4 to go to V5, 1, and then this one CS, this one is G3, and then from here we have this one V8, this one V8, -1, and this one is H3, and then V4, H2, and then V7 going to this one, put -1, and then another one here, H1, V6, go to V1, -1, -1. So this is the equivalent of signal flow graph from this block diagram. So I think I stop here first. We continue our class next week on Monday online, and then also on Friday for 2 hours online. Ada soalan nak tanya? Do you have any question you want to ask?